Barba from George Washington University. So Lorena Barba has been at the forefront of scientific computing for a number of years, doing lots of works on GPU computing, fast multiple methods, Navier-Stokes, but is also an amazing open source advocate. If you go to her homepage, you will see lots of activities around Python, Jupyter, strong activities on Python Jupyter conferences, and very much an amazing advocate for the whole infrastructure and open source software. Thanks a lot, Lorena, for agreeing to, well, virtually come here and talking to us today.
Thank you so much, Timo, for that introduction, and for everyone for showing up in this to this workshop. I know it's very hard sometimes to find space in now our blended worlds between home and work, and for me it was even just hard to comb my hair this morning and be presentable for a few seconds for you. And so thank you again. And what I wanted to share in this case is more of the story in my lab with one algorithm when we've been re-implementing this algorithm over and over again over many years, and to illustrate the sometimes tortuous progress in computational research. This is a story of a small-scale effort in one research lab with, just one PhD student coming after the other. And I think this is a story that speaks about the inherent tension between the student's goal, which are one-time use code, what I call performance brag, that is, you just want to get it to run faster than the next guy and get the thesis results, of course. And there's a tension between that and the goals of long-term reusable, sustainable software. And in this case, this is code that we're working on, we call it ExaFMM, and it is a new rewrite right now, a new rewrite of a high-performance implementation of the fast multiple method in C++. And my students and postdocs have written at least 7 separate code bases from scratch for this algorithm over more than 10 years. And we kind of hope that this is the last one, but I can't guarantee it. So ExaFMM is an open source library that implements the fast multiple algorithm. I'll explain the algorithm in a moment for those who are not familiar. It is an algorithm introduced to solve n-body problems. And the code, of course, we're aiming for parallel execution with GPU capability. And there are 2 common variants of hierarchical n-body algorithms. The fast multiple method, abbreviated FMM, is one. Tree codes are the other. They're similar in many ways. Both use tree data structures to organize the data for a particle situation, the source particles, to organize them in space into a hierarchy of cells. I'll describe this with a few cartoons in a moment. But what's interesting about the story of this algorithm, it was introduced more than 30 years ago. The FMM was cited as one of the top algorithms of the 20th century, up there with Monte Carlo and FFT, by some of the leaders in the community, in the CSC community. But unlike the FFT, for example, we don't have a standard library that people can use and incorporate in their application software. So this was one of our motivations. Oops, let's see if I can move forward. Okay, so let me just give you a cartoonish short introduction to what the fast multiple algorithm is about. So suppose that we want to calculate the gravitational influence of a great galaxy, say the M31 galaxy in the constellation of Andromeda, on Earth, Earth being, of course, in the Milky Way galaxy. Now, the number of stars in the Andromeda galaxy is 10 to the 12, so 1 million million. Okay, 10 to the 12th. But if you think about it, you know, looking up in the night sky and seeing an M31 galaxy in the distance, we really cannot distinguish individual stars. You just see a little fuzzy patch of light because the galaxy is at 2.5 million light years away. And so let's apply this intuition to gravity. And the idea is to substitute the whole Andromeda galaxy with a single mass point that is located at the center of gravity of the galaxy. And so here in the middle of this slide, let's see, I don't know if you see my cursor, I'm moving it around, that equation there on the top. Here is the form of the gravitational potential, where this K here is what we call the kernel. It's proportional to 1 over the distance between 2 points, the 2 points being xi and yi. And so suppose we want to calculate the effect of this Andromeda in our galaxy, the Milky Way, and astrophysicists know that if they want to calculate the interaction between two galaxies A and B that are very far away, they don't really need to calculate every single interaction between all pairs of bodies in the system. You can collapse the bodies in each galaxy into their center of mass and evaluate the potential due to one galaxy on the other's center of mass, and then use this result to calculate the effect on every local point. So this is an approximation, but when the galaxies are far away, it can be a good approximation. If they get close, the approximation deteriorates. So a key assumption then is that the galaxies A and B are well separated. So this is a three-step approximation. So the first step, we get the total mass of the galaxy B into the center of mass. So that is in the center of mass. So that is an order NB, NB being the number of bodies in the galaxy B, computation. Then we calculate the potential due to galaxy B on A, this A, center of mass of A, and that is an order 1 calculation. And then you calculate the shifted potential on each body of N, which is an order NA calculation. NA is the number of bodies in the galaxy A. So the process here reduced what was originally order NB times NA calculation to an order NA plus NB calculation. That's a tremendous speed up when there are many bodies. And of course, as I said, this is acceptable when A and B are well separated. Now, the second key idea of the fast multiple algorithm is performing in a hierarchical subdivision of space. So let's look at a cartoon here of a two-dimensional example, so flat land, a flat world. So suppose we have these few bodies, which are our sources of gravitational potential, and we want to build a tree of subdomains starting from the whole domain, which we call the root of the tree, or level 0 in this world. So that would be the whole domain. And then we divide recursively until, in this case, in this example, we finish when we have no more than one body in each subdomain. So this is a way that we kind of build boxes around the bodies, and we're going to use this information to find out when boxes are well separated. So the spatial decomposition then is related to a tree structure where level 0 has only one box, and that is the whole domain. As you can see, level 1 boxes would be they're next to each other, so we can't use any approximation. At level 2, we could use the approximation, but only for well separated boxes. And for those that are not well separated, you move down to the next level of smaller boxes, and now again you have some that are well separated and others that are not. So with this hierarchical process, you end up having a fixed number of boxes to look at to compute, in this case, in 2 dimensions. It would be 27. In 3D, it would be 189 boxes. So this is what constitutes a interaction list, and it is a constant size. But do note that, of course, course, the number of boxes grows rapidly with the number of dimensions. So this is usually we're talking about space, physical space, but in other type of applications, with many dimensions, things get more tricky. So the result of all of this combination of techniques is that you can get order n log n operation. And this is what's called the Barnes-Hutt algorithm. But the idea 3 in the fast multiple method is to reuse some computations. And so, you can compute the total mass of the parent from the children boxes at order 1 cost per box. Then standard nomenclature we use in the fast multiple method world is that we do P to M computations when we from these source particles get an expansion, and the M stands for multiple expansion at the center of each box. M to M represents a translation to the parent boxes, the larger boxes. We don't need to use again the source particles to compute the total mass of the parent box. We just use the already computed multiple at the lower level. M to L is an operation that is called multiple to local transformation when you compute the effect of the faraway boxes into the local boxes. Then local to local is again a translation where you're moving now from the parent boxes into the child boxes. And at the end of the whole process, you can compute the effect on the target particles via what's called the local to particle interaction. So this is in one cartoon, the illustration of all the computational kernels in the algorithm. Now, that was it. That was my flash description of the algorithm. And so let's talk about the applications in general for this algorithm. Fast particle algorithms like tree codes and FMM were first used in astrophysics, as in my description, to compute the interaction of many bodies under a gravitational potential. But in the integral formulation of problems that are modeled by elliptic partial differential equations, which lead to a numerical integration, as shown here at the top of my slide, they end up having the same form computationally as an n-body interaction. So this means that we can use n-body algorithms in a slew of applications, including acoustics, electromagnetics, and fluid dynamics, and even some algebraic applications as well. So that's the introduction, the context of this story that is really about software. So let's turn about the software and tell you a little bit about our lab-grown codes for this algorithm. And it all starts way back when my first PhD student started learning about this algorithm and wrote a two-dimensional prototype in serial called PyFMM. PyFMM is a Python implementation written just to learn about the algorithm using the simplest form of FMM, which is just a Laplace kernel. That is, we're solving a Poisson equation using Cartesian expansions because it is 2D. And it was the work of my first PhD student at Bristol University. And realizing how complicated it was to code up this algorithm, I was starting to get very concerned about the need for open source software in this field. Number two here, PetFMM is our second implementation developed by the same PhD student in collaboration with Matt Nepley, who was at the Pepsi team then and now is faculty at Buffalo. No, I think, yes, Buffalo. And with later contributions from my postdoc, Rio Yakoda. So it was first released with a paper in 2009 in the International Journal of Numerical Methods in Engineering. And it had an original feature as a serial implementation still by combining with optimization techniques from graph partitioning to then be able to propose a scalable parallelization. Now, one interesting aspect of this implementation was that it used C++ templates. So this was a decision made, by the group at that time, influenced by kind of the desires of the graduate student to learn about these things and the preferences of my collaborator, Matt Nipley. And so use C++ templates over the structure used to describe source and target, over the neighborhood stencil, over the expansion order, over the space dimension even. So imagine we have really in past multiple method applications in physics, just two dimensions, 2D and 3D. And those are two different code paths altogether. But they decided to template over that. So we learned later that was an over-engineered solution, hard to maintain. And when you get new graduate students coming into the group, nobody wants to touch it. So that was the reason why this code was essentially abandoned. So we wanted also to use GPUs, and PEDFMM number 2 in the list here made that difficult because of its hard dependency on PEDC. Also, my postdoc, Rio Ricotta, had joined the group. He hated reading through the templated code, and he could not reason about it. And the use of templates was just overdone. Lesson: there's no need to template over space dimensions. And so my postdoc Rio started a brand new implementation for us to study the use of GPUs. We called it GEMS FMM because it was produced to accompany a chapter contribution to the GPU GEMS book published by NVIDIA in late 2011. It is a CUDA implementation of the tree code and FMM for just Laplace kernels in 3D. And this is when we start accumulating knowledge in the group about GPU implementations of the FMM computational kernels. Some of these we reused until today or have been optimized. But this code was a serial 3D C CUDA code. So then we started this idea of the parallel ExaFMM code. We had a first version, alpha version, that was released at the time of the Supercomputing Conference in 2011, with a poster showcased at the NVIDIA booth. And this is the third implementation, right, of the FMM that even my postdoc had worked on. And we had a paper that appeared in 2012 in the Computing in Science and Engineering magazine. So in the meantime, I have another PhD student, Simon, who was later hired by NVIDIA as a dev tech, and he's not happy about the overuse of class inheritance in ExaFMM. Now, to confess, this had 11 levels of inheritance. So, my postdoc was learning C++ at the time, and he was just wanting to use all the bells and whistles. So my other PhD student could not deal with that, the Russian doll of class inheritance. And so in his thesis, he used yet another implementation, number 5 in this list, of the FMM that reused only the kernels from ExaFMM but with a different tree construction. This code actually was done in collaboration with Chris Cheka. It's the 5th in our group. Chris Cheka also joined NVIDIA after he finished his postdoc. So, by this time, we're finally able to deliver high performance with ExaFMM. We have MPI parallelism, we have threading with OpenMP, we have the CUDA kernels for the most computationally intensive parts. And we had a paper showing scaling on, back then, the computer was called Kraken, Cray machine. And it was showing good parallel efficiency for then a non-SIMD code. Of course, non-SIMD means it's slower and it's always easier to parallelize slow code, as you all know. It was first released in 2011 and continued to develop until 2016. Now, it used a particular technique from parallel tree codes that goes all the way back to the original Salmon and Warren tree code. And I got the original Salmon and Warren tree code as a graduate student in Caltech from John Salmon himself, who was a physics student. Then he had graduated and gone on to work at Quant in New York or something. He was visiting. So I got that original code, and we were able to understand this parallelization technique called the local essential tree. I just wanted to share about this because it's interesting that this technique, published in 1993 in this paper, a parallel hashed octree n-body algorithm, you know, at that time, 1993, if you imagine, that's Beowulf cluster time, this big beige boxes connected by Ethernet. That was another time. And, but the technique of the time actually continues to be used until this day. And this paper was recognized with the Supercomputing 2018 Best Test of Time Award. So only 2 years ago, already it was recognized after 30-something years that this algorithm continues to be, this part of the algorithm, this technique continues to be impactful. So back to our version of the code, this is, as I said, first time we have a high performance, but it's over-engineered with many layers of class inheritance, and it's long and complex, 12,000 lines of code, hard to maintain. And my new PhD student in joining the group started to work with my postdoc Rio to write a new version that would be simplified in 2017. So that's what we call ExaFMM version 1. 8 months later, for my year 3, already experienced PhD student, and it's the 6th implementation of the FMM done in our group, 10 years separated from the first, and we now focus on good naming, good interfaces that match the mathematical equations. This code has no dependencies except for MPI and OpenMP, and it uses the standard library only. The same parallel strategy using the local essential tree that I described won the Test of Time Award, the same analytical kernels, and we added module level tests and regression tests, and it's simplified everywhere. Now modularized with the tree totally separate from the kernels, for example, and it ended up being 70% fewer lines of code. So this tale here gets to some lessons already. I think that here is when we are faced with this inherent tension between a student's goal of one-time use and performance brag and thesis results, and the goals of reusable, sustainable software. It's a really tortuous path to build a good piece of reusable software for a complex algorithm, and really unreasonable for one research group, even with the continued collaboration of the group members that leave. So I guess that's why NSF is hopefully now focusing on funding large software institutes. So now here we go to implementation number 7 of the ExaFMM in our group. Same student, 2 more years, and we're using the kernel-independent version of the algorithm. I didn't have time to tell you about its how it works, but the motivation to use the kernel-independent version is that it gives higher performance when you move to high accuracy, reflected in the code as high multiple expansion, high P. We say P is usually the variable or that we use in the equations for that. This is now, again, we've learned our lessons, showing shallow inheritance, conservative use of classes, clean function interfaces, and the goal is that it would be easy to extend. But we also want to maintain the performance, of course. So it has to be faster or competitive with state-of-the-art code that exists in this sphere. So I have just a couple of demonstrations of the performance. This is a single node performance, in this case, single precision. So using a single precision representation for floats on a 14-core i9, so with OpenMP. And this was done by my student Tinyu, and he should be in the Zoom as a participant, hopefully, and can join in the Q&A and in a moment. So as you can see here, we have the blue line, 0.5 seconds for 1 million sources. That's the total time, including what is this called the setup, that is the building of the tree and the interaction list. And on the right-hand side is just the evaluation of one pass. So without that setup, without the building of the interaction list and so on. So ExaFMM is faster than state-of-the-art at single precision accuracy. And this is a double precision accuracy. So this is getting 7 digits. And here we have ExaFMM competitive with state-of-the-art. This is our coach from other groups, PVFMM from the Georgia Tech group, GAL FMM from India, implementing what's called a black box FMM. And so we are now at competitive performance. We don't want to be slower. We want to be at least equal, as you know. And here we move to a test at high accuracy, meaning you're getting 10 digits of performance. Still competitive, but unclear what applications need this accuracy. Nevertheless, here we have it. And this is really exciting for us, the new development of our ExaFMM Python interface. So here, Tingyu used PyBind 11 to create Python bindings for the C++ code. And because of this wonderful tool, it was less than 400 lines to create the Python interface. And it allows using ExaFMM as a package with, for example, NumPy arrays for the sources and targets to start with. It gets the same performance. And really, it's possible to do that because ExaFMM only uses standard C++ containers. So it makes it straightforward to create that Python interface with PyBind. It allows you to use pip install and with a setup script that will compile ExaFMM locally. Everything, of course, open source and available on GitHub. So now this is my favorite slide, that we can now use ExaFMM in a Jupyter notebook. And we have some examples, and we plan to develop more examples, making it easy to use this very complex algorithm with high performance still. So I'm going to end very soon and for our discussion, but let me share some of the thoughts that we have about this experience. You know, we have an important and complex algorithm that lacked a mature software library. So we decided, let's fix that. 10 years later, we learned a few lessons. The big challenge is that in a research setting, we're usually developing software by the combined work of a string of novice developers. Novice developers tend to over-engineer, and they tend to skip essentials like documentation, modularization, and robust design. And over-engineered code is the worst for research computing. We need code that is simple, modular, testable, readable, and can allow long-term use by the community. Another challenge is that testing is hard in research computing. You can have, you want to test in different hardware. You know, you're going to move to a cluster that allows you to use the top machines with you want to use vector operations and so on. You'll encounter different compilers. You have to test edge cases. And so the lesson here is that in computational research groups, we really have to implement code review as a regular practice. We want our goal to be code simplicity and high performance. And believe it or not, for many in this call, maybe code review may be an obvious thing to have to incorporate. But in practice, when the rubber hits the road, you know, that's not yet a regular practice in the majority of computational groups that I know. So let me tell you just thought about cost of this story that I shared with you. I suppose this has been funded by the Faculty Startup Fund, you know, my first job at BU, the NSF Career Award, and we have a couple of small awards like a Massachusetts Green High Performance Computing Consortium small award for the collaboration with Chris Cheka. I don't know, let's estimate, give it a ballpark of $1 million, 10 years, you know, and a few papers in comparison to maybe groups that do a lot of other kind of work that doesn't require this torturous software engineering. and rejections, because you have some improvements that are considered not novel enough. We have some rejected papers sitting on archives that we are proud of, but our reviewers would not let through. So that's upside down smiley, but well, something to consider is that there is also a benefit to lab members. This is an educational effort, and we deliver highly trained people to the science and technology world. My PhD student number 1 who worked on this project is a staff scientist at the Swiss National Supercomputing Center right now. Postdoc is now faculty at the Tokyo Institute of Technology. PhD student number 2 that worked on this is a DevTech engineer at NVIDIA. Our collaborating postdoc is also, he's in research at NVIDIA. And PhD student number 3 is graduating soon, so I recommend that if you have a project, you hire him. And with that, I want to end with a link to our website and our GitHub group. And hopefully you have some questions or comments. I'll stop sharing now. Actually, I'll leave the sharing on in case you want to see any other slide, or I can share again. Just let me know if there are questions.
Thanks a lot, Lorena, for this very wonderful and insightful talk. It's very nice to finally see something where people talk about the development towards the code and not just the results. We have no questions in the Q&A yet, so let me maybe start with one question. I mean, you now have a very nice compact code, but how do you want to avoid code bloat in the future? I'm just thinking about at some point you might want to add some CUDA functionality again, or maybe some circle functionality, then some different kernel types. And quickly you might end up with something that really resembles like your original 2005 code again. So how do you want to avoid these kind of bloat developments?
Bloat is the word you used?
Yeah, well, in bloat in the sense
or is the word I heard?
Code.
Bloat is the word I heard, yes.
Yes, in the sense that
well,
you throw in
have
more and more functionality, yes.
Yes, we have the kernels for the CUDA. We have the CUDA kernels available. We have already the experience in the group for the MPI using local essential tree and some other techniques as well. And my student is working adding those back in. Well, we maintained the goal of being able to use this from Python and being able to allow people. Now, if you make the code easier to use and you demonstrate performance, at some point you allow other people to get results with the code without having to dig into the code itself. This wasn't the case before, right? But it remains that the complexity requires that you test in different architectures, that you have different components. We do have continuous integration. We do have a testing regime to make sure that things compile in a set of different machines. There's a constant tension between enlarging, the scope and keeping things simple. And there's no, I don't have an answer to that. But you have, I think, to keep always in mind that the code development should continue in a process that is less prone to turn into spaghetti code, right? Doing code reviews, making sure other people in the group are able to understand what was done, doing the continuous integration, checking for accuracy, checking that performance is maintained over time. And the next thing is enlarging our collaborator space so that we get more input into software.
So we've got a question here by Adrian Jackson. So in hindsight, do you think PhD students particularly should maybe target more generic software to spend less time focusing on machine-specific details?
I've try to stop PhD students from getting carried away with things like what will get them the next performance so that they can brag about it. And it doesn't quite work. They will do it anyway. So the best you can do is keep talking to them and trying to keep some sanity in the whole enterprise. And you do, I guess, that by having people work together, but you know, having other people trying to check the new developments. And I think what we need to do is develop as a community certain practices and standards that are not yet widespread. Currently, even in my own university, other groups that do computational work, they don't have an onboarding process for new PhD students where they learn essential skills like version control, code review, continuous integration, and these lessons that I was sharing with you are not discussed with these students early on. And we really need to start developing that kind of minimum syllabus of the computational science field. I don't think we have that.
Okay. So do
you agree, Timo? Do you agree with that?
Actually, I do. Yes, and I'm really pleased that you're sharing these kind of developments, because it's a problem that we're all facing all the time.